Hello everyone. So today we are going to start our question paper solving session of Cambridge 9702 October November 19 variant 42. Okay, so let's begin. So our first question says about the Newton's law of gravitation. Now you already know that the formula for the Newton's law of gravitation is F equals to G into m divided by r square. Okay, so m divided by r square. Now from where how does the formula make sense? Okay, let's look. So okay, for example, these are the two objects. Its mass is capital M and its mass is small m, and the distance between their centers, okay, is r. So the force of attraction operating between them, which is the F, and which we are calling it as the force of gravitation, we can write it as F equals to G m divided by r square, and this is the Newton's law of gravitation. That means the force of attraction is directly proportional to the product of masses, and the force of attraction is inversely proportional to the distance between their center of masses or their center of gravities. Okay? So now let's go to the next question. The astronomer Johannes Kepler showed that the period t of rotation of a planet about the sun is related to its mean distance r from the center of the sun by the expression r cubed by t square equals to k. The question tried to say is like, for example, this is the sun, all right, this is the blazing sun. Okay, and let me draw some orbits like this. Okay, these are the orbits and these are the planets in the orbits. Okay, so uh, uh, so as the question said that the planets are rotating around the sun. Okay, the planets are rotating around the sun. So since the planets are rotating around the sun, that means they must take a certain time to give one complete rotation around the sun, which we are calling it as the time period. Okay, so for example, for this planet, the distance of the sun, the distance of the center of the sun to the center of the planet is r1, and its time period is t1. For this planet, from the center of the sun to the center of the planet, the distance is r2 and its time period is t2. So the question tried to say that radius cube or the distance cube will be directly proportional to the time period square for all planets. Okay, and finally what you might say is that r cube by t square is equal to constant for all planets. Okay, which further means that r1 cube by t1 square must be equal to r2 cube. I'm sorry, I'm having difficulty to write the cube here, divided by t2 square. Okay, that's what the question means, and now you have to show that this is the case. Okay, now imagine, so when you are trying to derive some formula, just bring in all the cases and try to make sense of finding equality between two or more quantities in terms of something. Okay, for example, in this case, in this case, Earth or any planet is rotating around the sun. Okay, so consider this is the sun. Okay, this is the orbit of a planet. Okay, this is a planet. This is a distance between the center of the sun to the center of the planet. All right, and the time period of the planet rotation is t. Okay, now tell me, for instance, that which force is operating between the sun and the planet. Which force is operating? The operating force is the force of gravitation between the sun and the planet. And the Newton's law says that the force of gravitation in case of both the objects that are attracting each other, it would be equal. Okay, so the force of gravitation, this is the force exerted by the earth on the sun. Okay, and this is the force of gravitation exerted by the sun on the earth. And according to Newton's law of gravitation, the force would be equal, isn't it? The force would be equal, which means force exerted by the sun on the earth, this must be equal to force exerted by the earth on the sun. Okay, so these two forces would be equal. And now let's apply the formula for the force of gravitation. So the formula for the force of gravitation would be F will be equal to, suppose capital M is the mass of the sun, small m is the mass of the planet, gmm divided by r square, where r is the what you call, r is the distance between the center of the sun and the center of the planet. Okay, so now let's go to a second factor. Now let's go to a second factor. Okay, the second thing is that, did I start the video? Yes. The second thing is that this is the sun. Okay, this is the orbit, and this is the rotating planet. Okay, so the planet is rotating around the sun. That means the planet, and you know that any rotating object must experience a force towards its center of rotation, and this force is what we call the centripetal force. Okay, now here is what we know, that you must have an important concept for the centripetal force, which is that centripetal force itself, the centripetal force itself has no existence at all. Okay, any force that causes rotation can be considered as a centripetal force. There is no related physical quantity, or there is no any physical factor which is can be called as a centripetal force by itself. But anything that causes a rotation of an object, any force that causes rotation of an object or is responsible for the rotation of an object, is known as the centripetal force. Okay? For example, suppose what can you say, that this is your finger. Okay, I'm not very good at drawing, and here is a rope tied, and you are just rotating a stone around your finger. Okay, so here the tension force in the rope, is creating the centripetal force. Okay, so here in this case the tension would be equal to the centripetal force. Okay, okay, now In this case, the force of gravitation between the sun and the planet is responsible for the creation of centripetal force on the earth. Okay, so we can say that force of gravitation of sun on the earth is responsible or is equal to the centripetal force on the earth. Okay, and do you remember the formula for the centripetal force? Let me tell you, if you do forget, the centripetal force is equal to m omega square r, where omega is the quantity which is known as the angular velocity, or if c is equal to mv square by r, where v is the speed of the rotating object. Okay. Okay, so let's use this formula, or we can use any one of them, both are applicable, no problem. So okay, so force of gravitation would be gmm by r square, and centripetal force is m omega square r, and you know omega has got the formula, it's the angular velocity, that means it is the angle covered divided by the time taken. Okay. Okay, so m gets cancelled out, and you put the value of omega here. The gm by r square would be equal to omega square r. So copy up to this place, and then gm is equal to omega square r cube. Now you put the value of omega, which is equal to 2 pi by t, and you will finally get that r cube by t square is equal to gm by 4 pi square. And you know g is the universal gravitation constant, m is the mass of the sun, which is not going to change, and 4 pi square is a constant number. That means the whole thing is a constant. So you can write that r cube by t square will be equal to constant. Okay. So here we have some more important formula, like gm is equal to omega square r cube. This formula is very important, and using the same logic you can go to the derivations of many formula. Okay. For example, if you use that force of gravitation, that means gmm by r square would be equal to mv square by r. Here you will get a formula for the velocity of the rotating planets. Okay. Now, okay, a satellite is in a circular orbit around the Mars. Okay, so it's a satellite which is in a circular orbit around the Mars. The radius of the circular orbit of the satellite is 4.38 into 10 to the power 6 meter, and the orbital period is 2.44 hours. Okay. Use this expression in B to calculate the value for the mass of the Mars. Okay. So what quantities you are given? You are given the radius of the satellite, you are given the orbital period. Okay. And now you have to calculate the value for the mass of the Mars. Okay. Okay. So is the mass of the sun given? Let me see. Mass of the sun is not given. I think we also don't need the mass of the sun, but we can do it simply because this question appears just after this question in the same number, in the same question number. So there must be a link between these questions. Okay, let me see. So what was the formula we have arrived? We have arrived that K is equal to R cube by T square, okay, and this K is also equal to Gm by 4 pi square, okay. So what we have got? We have got R cube by T square equals to Gm by 4 pi square, okay. So we are given the radius, isn't it? No, we are not given the radius. No, radius is given, all right. We are also given the time period, which is the hours, but we have to convert it to seconds. We are given the mass of the mass, and G, the value of G will already be given in the question in the first 2 pages. Now just put these values to find the value of M, okay. So you have to find the value of M, and all the values you know, okay. Now just find the value of M. Look, I think the value of G is given over here, okay, here, okay. Okay, so that's question number 1. Now let's go to question number 2. Okay, so smoke particles are suspended in air. Okay, Brownian motion of the smoke particles are seen through a microscope. Okay, then what is seen through a microscope? You already know about it, okay, and you already know that when you are observing a Brownian motion, then you observe that bright points, bright particles are moving all around in a haphazard manner, okay, following no specific pattern. So this is what you observe, okay. And how does Brownian motion provides evidence for the nature of the movement of gas molecules? So you know that during Brownian motion, what happens is that, suppose this is a very large smoke particle. So smoke particles are hit from various sides by air molecules, okay, by the air molecules. So what happens is that this smoke particle starts to move in a random haphazard manner like this, okay, in direction it likes. So we can say that in gas the particles move randomly, isn't it, following no specific pattern or no specific direction, and they have different velocities. They have high velocities, they have random velocities, whatever you want you can write, no problem. Okay, this question is quite basic. Now it's a question of thermodynamics, I think so. A fixed mass of ideal gas has volume 2.4 into 10 to the power 3 cm3 at the pressure of 3.51 into 10 to the power 5 Pascal and a temperature of 290 Kelvin. The gas is heated at a constant volume until the temperature is 310 Kelvin at a pressure of 3.75 into 10 to the power 5 Pascal. Okay, so the thing is that a mass of gas is heated to from 290 Kelvin to 310 Kelvin, but the volume of gas and the pressure of the gas remain constant. The gas is just heated, okay. The quantity of thermal energy required to raise the temperature of 1 mole of gas by 1 Kelvin is constant at constant volume is 12.5 joule, okay. So what is the quantity? Let me make it a constant. So thermal energy, which is 12.5, required to raise the temperature of 1 mole of gas. That means it should be mole, joule per mole gas by 1 Kelvin. Okay, so per Kelvin. So it's 12.5 joule per mole per Kelvin, okay. So that is the thing, Okay. Now calculate to three significant figures the amount in moles. Okay. So now you have to calculate the amount of gas in moles. So you know that we have a formula. Shit. Okay, so the pressure must be in the Pascal unit, which is already here, isn't it? The temperature must be in Kelvin unit, which is already here. Okay, and the volume must be in meter cube unit, but here it's in cm cube. So you have to multiply 10 to the power minus 6 to convert this value into meter cube. Okay, now put all these values into the equation PV equals to nRT. Okay, PV equals to nRT to find the number of moles of gas. Okay, now you might argue that here the temperature is 290 Kelvin, and here the temperature is 310 Kelvin. So which number we are going to take? Okay, so it's better that the starting point is better to always take the starting point from where you are starting. It's a 290 Kelvin. Okay, although if you take the later value, the value of mole will not differ by that much. It will just differ by some decimal points. Okay, so that will not be a problem. Okay, so the if you put all these values together, the temperature you may use as a 290 Kelvin, or you may use the 310 Kelvin, anything you may use. The number of moles will appear to be almost 0.35, something like this. Okay. So our next question, calculate the thermal energy transfer during the change. Okay, so what was the constant we had? We had the constant 12.5. Let me rub it. 12.5 for 1 mole for 1 Kelvin. Okay, but we don't know the amount of heat supplied here, but the number of mole is 0.35 and temperature change is 20 Kelvin, isn't it? If I'm not wrong, it's 20 Kelvin, but I can't put a 0 over here. Okay, into 20. Okay, so if you put the value in this way, then you will find the value of x. Okay, so mole, temperature change, heat energy change. Okay. Okay. Okay, so our next part. So I think the answer should be, let me see the MS mark scheme. What's the answer? So the answer should be 87.3, or it's about 87.5. Okay. Okay. Now let's go to the next question. For the change in gas in B, state the quantity of external work done on the gas. Okay, so how much work is done on the gas? Okay, so you know that formula for work done is work done equals to pressure into change in volume. And if you are talking about the work done on the gas, as we always say, work done on the gas, this is equal to pressure into volume initial minus volume final. Okay, but here there is no change in volume, so no work is done on the gas, so that's why work done on the gas is 0. Now the change in internal energy with the direction of this change. Okay, This is the first law of thermodynamics, that change in internal energy must be equal to amount of heat supplied on the gas plus work done on the gas. This is heat supplied to the gas, okay? This is work done on the gas. This has got signs. Okay, if you supply heat to the gas, then its sign will be positive, and if you take heat away from the gas, that means the temperature of the gas reduces, then its sign will be negative. If you do work on the gas, then the sign will be positive. If the gas does work on you or on the system, then the sign will be negative. Okay, so what was the change in internal energy? So change in internal energy equals to heat energy supplied, which is 87.3 or 5 plus work done on the gas. So it is 87.3. Okay, let me check the mark scheme. Okay, 87 point, so 87.3 or 87.5. Okay, so when you are talking about the direction of the internal energy change, it's actually asking to you about whether the internal energy is increasing or decreasing. Okay, so here the internal energy is increasing, since the value shows positive, so the direction we would say that it is increasing. But if the overall value was negative, we would say that internal energy is decreasing. Okay, now let's go to question number 3. Okay, so question number 3. State what's mean by specific latent heat. You know that specific latent heat means amount of heat energy needed or change in heat energy that is needed to increase the or to change the temperature of 1 kg of a substance by 1 degree Celsius, okay, or 1 Kelvin. So this is the specific latent heat. Oh, sorry, it says specific heat capacity, but the question says specific latent heat. Okay, just forget it. Specific latent heat. Okay, so latent heat is the quantity that appears when there is a change in state. That means from solid to liquid or from liquid to gas. When the state of the matter is changing from solid to liquid or from liquid to gas, the heat energy that is absorbed, is not used to raise the temperature of the substance. Rather, it's being used to break the bonds or break the attractive force between the molecules or between the particles. Okay, so that's why it's called the latent heat. Latent means actually hidden, because the heat energy you are supplying does not cause a rise or a change in the in the temperature of the substance. Rather, it changes the potential energy of the particles. So that's why the heat appears to be hidden, and that's why the amount of heat supplied during the change of state is known as the latent heat. Okay, so the specific latent heat is simply, so the specific latent heat, the specific latent heat is simply, specific latent heat is the amount of heat energy supplied for the change of state for 1 kg of the substance. Okay. Okay, so next, a student uses the apparatus illustrated in figure 3.1 to determine the value of the specific latent heat of fusion of ice. Okay, so a balance reading measures the mass of beaker and the melted ice water. Okay, in the beaker, the heater is switched on and pieces of ice at 0 degrees Celsius are added continuously to the funnel, so that heater is always surrounded by the ice. Okay, okay, that's a good thing. The heater is switched on, sorry, The water drips out of the funnel at a constant rate. The balanced reading is noted at 2-minute intervals. After 10 minutes, the current in the heater is increased and the balanced readings are again taken for further 12 minutes. Okay, so here we have different cases. We have two different cases. One is at a lower current and another is at a higher current. Okay, and the first reading was for 10 minutes and the second reading was for 12 minutes. Okay, the variation with the balanced reading is shown in figure 3.2. The readings of the ammeter and the voltmeter are shown. Okay, so from 0 to 10 minutes the ammeter reading was 1.8 and voltmeter reading was 7.3, and after 10 minutes the ammeter reading was 3.8 and voltmeter 3.6 and voltmeter reading was 15.1. Okay, now, and this is the graph that they were talking about. Now what is the data? From 0 to 10 minutes, 65 gram of ice has melted. Is that so? 0 to 10 minutes, 65 gram of ice has melted. I'm not sure. Let's see. Let me zoom it. So 8. So this is 9. This is 10. No. So this is okay. Each and every square is 0.4 units. Okay. So we have 0.4 units per squares. Okay, so from 8 to 10 we have to go 2 units. So 2 units, so 0.4 units for 1 square. So 2 units for how many squares? Let's see. So x equals to 2 by 0.4, which means 5. So we have to go 5 squares to get 10 from 8. Okay, so here is the 10. So in this, what is the mass of the mass balance reading shown? It is 100, 105. Okay, 100. Sorry, it's 110, 105, 110, 115 and 120. So this is 120. Okay, this is 120 and this is 55. So from 55 to 120 it should be 120 to 55, so 65 gram. Okay, so initial beaker reading was 55 gram, final beaker reading was 120 grams. So the change in mass of the beaker was 65 gram. That means we have got the 65 gram of water melted in the 10 minutes. Okay, so that's true. So use the diagram in 3.2 to determine the mass of ice melted in the 12 minutes to 22 minutes. So 12 minutes to 22 minutes. Okay, so that means they want us to start from here to 22 minutes. That means more 2 units. So we have to go 5 units. Okay. So let's see. In the 12 minutes, our reading is about 145. Okay. So in the 12th minute, our reading So in the 12th minute our reading was 145 grams in the beaker. Okay, and then in the 22nd minute, so 3 1 2 1 2, let me zoom it. So here 1 2 3, 3 units down. Okay, 3 units down from what? From 300. Okay, so in the y-axis our each square means 5 units, so 3 square means 15 units. So 300 minus 15, it should be 285 grams. Okay, so we have in the 22nd minutes we have 285 grams. So how much water has been melted? 0 4 1, 140 gram of water has been melted. Okay, so the answer to this question is 200 and what? Sorry, 140 grams. Okay, now explain why, although the power of the heater is changed, the rate at which thermal energy is transferred from the surrounding to the ice is constant. Okay, now this is a very important question. Okay, so the flow of heat from one region to another region depends on the temperature difference between the two objects. Okay, now look here, we are adding ice continuously. Did I turn on the video? Let me check. Oh yes. So here ice is added continuously into the system, and you know that ice is at a temperature of 0 degrees Celsius. Okay, all right. Now since the ice here is always at 0 degrees Celsius and the temperature of the surrounding is at a fixed value, or the temperature of the surrounding is fixed, so the temperature difference we can call it as the delta theta. The temperature difference between the surrounding and the ice is also fixed. Okay, so that's why the rate of flow of heat energy from the surrounding into the ice is also fixed. Okay, so that's why maybe maybe you are changing the power of the heater or the current from the heater from one value to another value. That means the heater may be supplying heat at a different rate to the ice because you have changed the power, but the surrounding is supplying heat at a constant rate into the ice. All right. Okay. But what was the question? Okay, so that was the question. So what should be the answer? That since the flow of heat depends on the temperature difference, and here in this case ice is always at 0 degrees Celsius and the surrounding has a fixed temperature, so the temperature difference between the ice and the surrounding is also fixed, so surrounding is supplying heat to the ice at a constant rate. Okay, now determine a value for the specific latent heat of fusion. Okay, now the thing is that just be careful that here the amount of ice that is melting is not only due to the heat from the heater. All right, so here what's going on is that the surrounding is also supplying some heat into the heater, supplying some heat to the ice, and the total amount of water we have got here is thus the result of heat from the heater plus heat from the surrounding. Okay, so this amount of water that has melted is the result of both the heat from the heater as well as the heat from the surrounding. All right, now let's apply the logic into this question. Okay, so determine a value for the latent heat of fusion L of ice, specific latent heat. Okay, now For example, for the first 10 minutes, uh, let the power of the heater was P1 in the first 10 minutes, and after the current has increased, let the power of the heater in this case be P2. I'm just first showing you the logic, the mathematical logic, then I will go for the detailed solving. Okay. So now you know that energy supplied by the heater is equal to power into time. You already know it, and you have been studying this senior since your lower secondary or O levels. Okay. Now you know that energy is equal to power into time. Okay. So in the first, so heat supplied in the first 10 minutes when the heater was at a lower power is E1 is equal to P1 into 10 into 60, because 1 minute has got 60 seconds. Okay. So P into T, and let the total amount of heat gained by the ice in the 10 minutes is therefore E1 plus heat energy from the surrounding in 10 minutes. Okay. Please note it down. I'm erasing it. Okay. Now in the next 10 minutes, let the power of the heater was P2. All right. And therefore the energy supplied by the heater in the next 10 minutes is P into 10 into 60. Okay. And the amount of water that has melted is the result of the heat energy E2 from the heater and the heat supplied due to surrounding in 10 minutes. All right. Okay. Now so we will be evaluating these two together by you already know the total amount of heat gained by ice or gained by a substance is the product of its mass and its specific latent heat of fusion, okay, or latent heat of vaporization. So now let's calculate the total amount of heat gained by ice in the first 10 minutes. Okay. In the first 10 minutes, okay, the first 10 minutes. So in the first case for the heater, when the power was P1, so that means in one case you have to be careful that amount of heat, I'm writing over here, the amount of heat gained by object during melting or boiling is equal to mass into specific latent heat. It's not the amount of heat energy supplied to it, it's the amount of heat energy gained by a substance, okay, which may be from one source or which may be from different source. For example, suppose the rate, okay, let me change the color. So the total amount of heat energy gained here would be, suppose its mass is m, no, let me change the color. Suppose its mass is m, specific heat capacity is L, so total amount of heat energy gained is m into L, okay, and the total amount of heat energy given to it is 2 red and 3 purple. So 2 red plus 3 purple, okay. So you have to remember this. Okay. Now in the first 10 minutes when 65, what? Charging problem. Okay, fixed it. So in the first case, the for the 65 gram, let me go to the data here. Oops. So okay, this is the first case, this is the second case. So in the first 10 minutes 65 gram of water has been melted, and 1.8 in 7.3. So you know that the formula, that P equals to VI. So the power is 1.8 into 7.3. So this is the power, the first power. The time was 10 minutes. So P into T. This is the T. This is the heater's energy supplied by the heater, and let the energy supplied from the surrounding is HS, or heat from the surrounding. Okay, and this will be equal to the energy gained by the ice. 65 gram of ice into L. Okay, and L has the unit joule per gram. Okay, so this is for the first 65 gram. Please note it down. Now for the next 140 grams, the current was 3.6 and voltage reading was 15.1. So P equals to VI, you already know it, and energy is equal to power into time. Energy is equals to power, which is 3.6 into 15.1, V in I into V into time for 10 minutes, 60 into 10. Okay, so this value plus heat supplied from the surrounding in 10 minutes, this will be equal to the mass of water melted into specific heat capacity. Okay, so here we have two equations. Now from the two equations, you have HS and you have L, two unknowns, so solve them simultaneously to get the value of L. Make HS the subject of the formula in each case, and then find L. Okay, and the final value of L would appear to be 330, isn't it? 330 joule per gram. So L will be equal to 330 joule per gram. Okay, now the next question said about what is the rate at which thermal energy is transferred from the surrounding to the ice. Okay, so since you have found the value of L, which is 330, now put the value of L in either the equation of 65 grams or the equation of 140 grams to find the value of HS. That means the heat energy supplied in 10 minutes. So the rate will be equal to heat energy supplied divided by time, 10 minutes. Okay, so 10 into 60 to get the value of rate at which heat energy was supplied, and this value would be 23. Okay, so this value would be 23 watt.